As I mentioned at the beginning of the previous section, we are going to generalize Green's theorem to other settings, and the role of this quantity, the partial of q with respect to x minus the partial of p with respect to y, that is going to be replaced by things that are called the curl and the divergence of a vector field. Okay, so let me explain what these concepts are. So what is the curl? We start with a vector field f, and the curl of f has this complicated formula that I don't remember. But instead of remembering it like this, if you look at this, you might think, well, that looks like the formula we use for a cross product. And it is, in fact, a cross product of the following. So the gradient, we've done the gradient of a function. We had, in the past, the gradient of a function was the partial derivative of f with respect to x, partial of f with respect to y, partial of f with respect to z. So if you consider the gradient just like we consider a derivative as an operator, we also have the derivative of x applied to a function. You can think of this as the gradient applied to a function. So we can isolate this gradient as this operator on functions, where in this case, when you do the derivative of a function, you get a function. But when you do the gradient of a function, you get a vector field. So this gradient is an operator that returns a vector field. And it's just a vector of derivative operators. And the curl can be defined as the cross product of this gradient operator cross a vector field f. So if I do that, remember the formula for a cross product, I put I, j, k, the unit vectors of a standard basis of R3. And then the second vector is this vector, which is just a vector of operators. And f is given by coordinates p, q, and r, which are functions of x, y, and z. So I put it here. And when you do the formula, now I follow the formula of the cross product, remember that the formula was, this is going to be a vector, and this vector is I times the determinant of this minor, and that is going to be this times this, so the partial of r with respect to y, minus the partial of q with respect to z. Now, this one is going to be, you go here and do this times this, minus this times this, and I like it better if this was written as we do with cross product, which was minus in cross the derivative of x with respect to x of r minus the derivative in z of p. Okay, remember that in the cross product is plus I minus j plus k, and then the coefficients in front of I, j, and k are some determinants. In any case, that is a formula for the curl of f that I think it's a little bit easier to remember if you just remember how to do cross products. So let's find a curl of a vector field. So here is a vector field, and I'm going to find the curl of f, and that is, by definition, I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and then x, y, z minus y squared. So it's going to be equal to, in I get this minus this. So the derivative with respect to y of minus y squared, which is minus 2y. minus the derivative with respect to z of xyz, which is xy. Now, minus, there's going to be a quantity in J, and that quantity, if I remove the column in J, is going to be this quantity minus this quantity. So it's going to be the derivative with respect to x of minus y squared, which is 0, minus the derivative with respect to z of xz, which is just x. Okay, and then plus a quantity times k, and the quantity times k is going to be, if I just want to mess this even farther, is going to be like this. So it's going to be the derivative with respect to x of xyz, which is yz, minus the derivative with respect to y of xz, which is 0. So all in all, when I simplify, I get minus 2y minus xy I plus xj plus yzk. Or if you prefer to write your vector fields as a vector, as I do, it's that vector field. Now, it turns out that with this definition of curl, if you do the curl of a gradient vector field, you get identically 0. Why is that? It's again a consequence of Clairaut's theorem, because if I try to do a curl of a gradient, then the third vector will also be a vector of partial derivatives of a function f. And when I hit it with partial derivatives like this, the coefficients that you get from the formula for curl are differences of mixed partial derivatives. But by Clairaut's theorem, all those mixed derivatives are equal if I do with respect to x, then with respect to y, or if I do with respect to y, then with respect to x, I get the same thing. So this is 0, and that is 0. So I get 0. So it turns out then that if I have a function of three variables that has continuous second order partial derivatives, then the curl of a gradient is 0. And I can use that to show that some vector fields are not conservative. This would be conservative if f was the gradient of a vector field, but that would say that the curl of f, which is the curl of a would-be gradient, would be 0 because of what I just said. So if I compute a curl and I get something that is not the 0 vector, that vector field could not possibly be conservative. Okay? So in this case, we have just computed that the curl of f is something like minus 2y minus xy xyz. It is not the 0 vector. That says that f is not conservative. Okay? That's a vector field we just computed the curl of. So by computing a curl, is one way to check whether something is conservative or not. And in fact, it is an if and only if I have a vector field whose component functions have continuous partial derivatives, and the curl is 0, then f is conservative. Okay, so if I find a vector field whose curl vanishes, then it has to be a conservative field, and I'm going to be able to find it expresses as a gradient. And remember that was beneficial because of the fundamental of line integrals, then tells me that computing line integrals of a gradient was very easy. So let's show that this vector field is conservative. And what I'm going to do is calculate the curl and hope that that is 0. So let's compute another curl of f. In this case, again, this is I, j, k partial with respect to x, partial with respect to y, partial with respect to z of the functions that appear in the coordinates. And I get the following. The partial with respect to y, so this will be this minus this. The partial with respect to y of this function is 6x y z squared. And the partial with respect to z of 2x y z cubed is 6x y z squared. So yes, that is 0. Minus, in j, what do I get? In j, I'm going to get this one minus that one. The partial with respect to x of 3x y squared z squared, that is 3y squared z squared, minus the partial with respect to z of y squared z cubed, that is 3y squared z squared, which again is 0. And then in k, it's going to be this minus that. So it's going to be the partial with respect to x, that's 2yz cubed, minus the partial with respect to y of y squared z cubed, that's 2yz cubed, which is 0. So this is the 0 vector. And that tells me that it is a conservative vector field. A vector field, the curl is 0, it is conservative. I'll talk about what is the interpretation of the curl. There's some, as you can imagine, it has something to do with rotations. We'll talk about that in a moment. So now, since I know that this vector field is conservative, I want to find little f such that the gradient of f is capital F. Remember that this came up when we were doing line integrals. We needed to do this to be able to evaluate line integrals directly using the fundamental theorem. So I need a function f such that this is the partial with respect to x of f. This is the partial with respect to f of y. And this is the partial with respect to f of z. Okay? So what I can do is take one of those and integrate. So f should be the integral with respect to x of y squared z cubed dx. And if I integrate that, the integrand does not depend on x, so this is just x y squared z cubed plus a constant of integration. But this constant of integration can be a function now of y and z. Okay, so that is a constant of integration, but this is now possibly a function of y and z. So now I test what function could that be so that it works with the other derivatives. So now take the partial with respect to y of what I just found out. And what do I get? I get 2xyz cubed plus the partial with respect to y of the function of that function. But this has to be equal to this function. That's great because that is exactly what I already have here. So this has to be 0. So the constant, the function c actually should be constant with respect to y also. So this tells me now that the constant function is actually just a function of the z variable. But now if I do again the same process, but with respect to the z variable, then what I get is 3xy squared z squared plus the derivative of that function. And this has to be equal to this component, but that is exactly what I already have. So we can just set this to be exactly 0 and that constant to be exactly 0, and now we see that this function already works. Okay, so what I found is that the function x y squared z cubed has a gradient that is equal to the vector field we started from. So it is conservative. We already knew that, but now I can actually show you what the function is that it's equal to a gradient of. So somebody had already asked, what is the meaning of curl? So in terms of fluid dynamics, so when you look at a vector field gives you directions. At every point there is a direction, and you can think about that vector field as giving you some dynamics of, say, if there was a fluid or a gas in that 3D space, it's giving you how the fluid would move, right? So the curl at a given point, it's measuring whether there is rotational flow around that point. Okay, so if there is a rotational flow exactly in this plane, then the curl would point in the direction that is perpendicular to that rotational flow. And you can see that in this picture of a vector field, there are points where there is, for example, in this point, yes, there is some rotational flow around that point. In this point also, there is some rotational flow. So the curl would detect that the curl is non-trivial because there is some rotational flow around the points. But if you go to a point here, anywhere in this other picture, there is no flow happening in circles around any given point, and therefore the curl actually vanishes at every point on that plane. Yes, you can do the curl on two variables, and in fact, we're going to use it in a moment, the curl in two variables, by thinking as the vector field as being 3D, but the z component is 0 everywhere, right? So think of a 3D vector field, but we're just looking at what's happening in the plane xy, and suppose that that vector field has z coordinate equals 0 everywhere. Then I can do the curl, and in this plane vector field, the curl would point up or down, or it would be 0. And if it is sort of, what is this? This is counterclockwise, so like this, counterclockwise, the curl would point towards me in the screen, versus here, where the flow is clockwise, the curl would point down through the screen and down in the negative z direction. Okay? All right. So now a second object that we're going to be using, again, we're going to generalize Green's theorem into Stokes' theorem, that will be using the curl, and then the divergence theorem, which will be using the divergence. The divergence of a vector field is the following. So is the sum of the partial derivatives of the components. So the divergence of f is the derivative of p with respect to x plus the derivative of q with respect to y, derivative of r with respect to z. How do we compute that or remember that? If you remember again the gradient operator, then the divergence is actually the dot product. Let me write that here. This is the dot product of the gradient operator dot with the vector field. And just remember that curl of f was the cross product of the gradient with the vector field. Okay? So let's find our divergence what is the divergence? And again, the divergence will also have an interpretation in terms of fluid dynamics. The divergence is measuring how much flow is there at any given point. What's the flow? We'll get to it, but it's also some measure of the interpretations of fluid dynamic system of this vector field. So the divergence div of f is the dot product of the gradient with f. So it is partial with respect to x, partial with respect to y, partial with respect to z, dot with x, z, x, y, z minus y squared. So it will be the derivative with respect to x of the first coordinate, which is z, the derivative with respect to y of the second coordinate, which is xz, and the derivative with respect to z of the third coordinate, which is 0. So that is the divergence. Much easier to compute that a curl. Now, a similar theorem like we had before, the curl of a gradient vector field was 0. It turns out that the divergence of a curl is also 0. Okay? The divergence of a curl of a vector field vanishes. And that is, again, a consequence of Clairaut's theorem. If I just put everything, what everything means, if I compute the curl, remember, it has those 3 coordinates. And if I do the dot product with the gradient again, what I get is a sum, which is a sum of differences of mixed derivatives, which will vanish. So we get that the divergence of the curl is 0. So now, you noticed before that I was missing a t over there. Show that the vector field is not a curl. So I want to show that f cannot be a curl, and if it was a curl, if I take the divergence, it would vanish. So if f was a curl itself, then the divergence of f would be the divergence of the curl of G, and I know that the divergence of a curl is 0. So just compute the divergence of f and see what that is. If that is non-zero, then f cannot be a curl. But we have already done that. This is the one I just did over here. And it was x, xz, 0. So this is x, xz, 0 is non-zero. So f is not a curl. Okay? This is the equivalence of when we did the fundamental theorem of line integrals. We were trying to figure out, is this vector field conservative? Is it the gradient of some function? If so, then I can use it. If not, I cannot use it. So because f is not a curl, then we're not going to be able to use one of the theorems that will come up later. Okay, so just very briefly, because this one is not as well explained here, the divergence is also understood in the context of fluid dynamics because if f is the velocity of a fluid, then the divergence represents the net rate of change of the mass fluid flowing through a point per unit volume. So one way to know whether the divergence will be positive is to, if you trace the line of what is happening in the dynamics here, so if I look in here, what is happening dynamically is something like this, and you can see that the flow is less here than it is here, so the flow is increasing as we go by. The velocity is increasing in the paths that are defined by those by that vector field. So in there, the divergence is positive because there is that increase in flow. But if I do the same thing in this one, if I go along the paths that are defined by the vector field, it is in fact the flow is the same in those lines. It's faster here and it's slower here, but in the lines of the flow is constant. So the change of the rate of change is 0 because the flow is the same. So in here, what I'm saying is that if there is some speed of the flow here, here is faster, while here is slower, but in a given line, the flow is going at a constant rate, while here is accelerating, and the flow is going faster as you move away from the point. So that's what is measuring the divergence being some number or being 0. The last thing I want to say is one more operator that you may have heard about, which is the Laplace operator, which the Laplace operator comes about by doing the divergence of a gradient vector. So if I take a gradient vector and do again another gradient on it, so do the dot product, let's mark it as such. If I do the dot product of a gradient with a gradient vector field, then what I get is this, is the sum of the second partial derivatives, the second pure partial derivatives, and that's called the Laplace operator. And the Laplace operator in the Laplace equation has a central role in differential equations to study things like the heat equation, the wave equation. It's a very important operator. Again, in differential equations, if you go on to differential equations, then you'll see a lot of Laplace everywhere. And in coordinates, you can just take a vector field, and if you want to do the Laplace operator to a vector field, then what you're doing is just doing the Laplace operator on each one of the coordinates P, Q, and R. Okay, so I think, let me just finish up with reformulation of Green's theorem, which is the following. So if I have Green's theorem says something about these line integrals, about a closed path, C, of this integral. And what I was actually, because somebody asked, can you do a curl of a flat vector field, of a vector field in 2 dimensions? If you take this vector field in 2 dimensions and you think about it as a vector field in 3 dimensions, but the z coordinate is 0 everywhere, then you can do the curl of f, and the curl of f gives you this quantity that appears in Green's theorem. Okay, so the curl of f, thought about it as a 3-dimensional vector field, gives you this quantity times k. So it's the curl is pointing up or down, and what's the magnitude is exactly the quantity that appears in Green's theorem. So if I do the curl of f times k, then I actually get that quantity on the nose. So you can reinterpret Green's theorem, which is what we call a vector form of Green's theorem, as the line integral of this vector field is equal to the area integral of the curl of f dot k. So that is a way that we'll see that this carries over exactly to Stokes' theorem to vector fields in 3 dimensions. And in fact, we also can see how you can reformulate this in terms of divergence. If you take now the tangent vector and the normal vector, so the tangent vector to the curve is tangent, the normal vector is the one that is of unit length and perpendicular to the tangent line, then it turns out that similarly, like I did before, this quantity is actually equal to the integral, the double integral of the divergence of the vector field. and we'll see how these generalize in the Stokes and the divergence theorem.